Okay, this time. Okay, let's see here. One more thing. Hello, good morning and good afternoon and good evening. This is Paul Liu from North Carolina State University. Welcome you to the World River and Delta System Source to Sink webinar series. And this webinar series is co-sponsored by National Science Foundation and North Carolina State University, Louisiana State University, State Key Lab of Estuary and Coastal Research, East China Normal University, and Utrecht University. So today is our great honor invited Professor David Mosher from Geological Survey of Canada, also affiliate is Professor Lee, University of New Hampshire, come here talk about a river beneath the sea, actually a very deep sea, the Northwest Atlantic Middle Ocean Channel. So as the slide show, this is also a teamwork, come like a colleague from Sebastian Crystal, University of Kiel, Kai Bogild, also Geological Survey of Canada, and Christoph Stevenson, University of Liverpool, and many other colleagues. So before I introduce David, I would like to mention since the August 2020 and the start of the pandemic, everybody locked down at home, and we started this webinar talk series. So far, we have already hosted 127 talks. All those talks have been archived on our YouTube channel. This is the link, as you can see. Feel free to use them as a resources for your teaching and research. And as you can see, in the 2020 and 21, we have many topics already covered. For example, Amazon, there's more than 6 or 7 talks. And San Francisco, for example, Magdalena, Mississippi River, Yukon River, Mackenzie River, Congo River, and all the Asia, Ganges, Brahmaputra, Irrawaddy, Mekong, Yangtze, and all many global scale overall talks. But today's talk is a very special, interesting, because this is not a river channel on land, not simply a delta in the ocean. So, but at the same time, you will see, David talk, but at the same time, we also maintain a Source to Sink Twitter account. It's called Source to Sink. If you have a Twitter account, you're welcome to follow us. For example, we will announce every week our weekly talk on Twitter or some exciting research news or publication over that platform. And next week, next Wednesday, same time, Janok, also from Canada, McMaster University, come here, also talk about Source to Sink in deep time, reconstructing, the river in the to their catchment in North America. So please mark your calendar, also come here. As I mentioned, Dave Mosher is the Senior Research Scientist, the Geological Survey of Canada. As you can see here, he original graduate from Acadia University, Canada, and then get a master from Memorial University of Newfoundland, and then PhD from Dalhousie University, Halifax. And then, as you can see, several adjunct and also professor of University of New Hampshire, senior scientist of Geological Survey of Canada. At the same time, also serve commissioner on the UN headquarters for the continental shelf, limit of the continental shelf. David research mainly focused on the marine geohazard, including tectonics, submarine mass movement, and tsunami. And most recently, is extend to the deep water sedimentary process and continental evolution. And so the later kind of engage the more kind of law and international conflicts, particularly maritime boundaries. So I think, Dave, now I will give the floor to you. Please share your screen for the presentation mode.
Sure, Paul. I hope
It's good.
is that visible now?
Yeah.
And I'll put it in presentation mode, I hope. Okay, you're
Very
seeing
nice.
it okay?
Yeah, very nice.
Okay, great. Well, thanks for very much for the invitation to present this material. It's pretty exciting, and it stems really my entire career. I first surveyed across NAMOC as an undergraduate student in 1984, and vowed one day I would come back and map it in more detail. And now, towards the end of my career, I finally had that opportunity. So it's really exciting for me. So yeah, without further ado, we'll get on with the presentation. I first recognize my co-authors on this particular aspect of it. Sebastian Krastels with University of Kiel in Germany, and he and I were co-proponents on the leg to survey. And Kai Bogild is a former student of mine and now employed with the Geological Survey. And he's responsible for many of the technical aspects we'll show. Christopher Stevenson's at the University of Liverpool, and a student of Picoult's and a real expert on flow dynamics of these systems. In addition, though, we had a whole crew of students on board. We surveyed last summer, not at the height of COVID, but certainly COVID restrictions were in place. And so we had actually no other participants other than myself. And I was fortunate enough to be able to join in part due to vaccinations, and in part because the ship had to come into Canada to fuel, and they allowed me to get on, but they didn't allow anyone else. And even for the first 5 days or so, I had to isolate on board ship. So awkward times, but we had a great crew of students who formed most of our scientific staff, and they were very enthusiastic, and we managed to pull off this expedition. So we'll talk a little bit about an introduction, the history of exploration of NAMOC, some of our incentives to survey NAMOC, and something about the expedition on the Maria S. Marion, and then a bit of our equipment and methods that we employed. So look at some of the results, and then I want to focus on the river analogy and comparing this system to a river, and then what are the implications in a source to sink scenario. So this is NAMOC as we understand it today. It flows 3,800 kilometers from sort of northern Labrador Sea, seaward of Hudson Strait and Davis Strait. And it wends its way through the central Labrador Sea and circumnavigates the Grand Banks of Newfoundland. Ultimately terminates, or we think it terminates, at the sort of northeastern end of Somme Abyssal Plain. But that area is not well surveyed, and so that is an objective yet to be accomplished, I guess. We looked only at this northern portion. We had a little over a month of ship time, and in that time allotted, we weren't able to survey the entire thing. So we focused on the northern branch, and it's about 1,800 kilometers in length of the area that we were able to survey. We acquired multi-beam bathymetry, sub-bottom profiler, seismic reflection data, and gravity cores. This is just a perspective view then of Labrador Sea, showing that it's a rather bowl shape in its morphology. The NAMOC itself flows through the center of it, sort of the lowest point of the basin as expected. You see in the right just a hydrodynamic model. It shows many potential branches that could feed into NAMOC. This is opposed to, say, a conventional submarine fan that stems from a river system, in that there's generally just the one feeder region, one tributary area, whereas this one has the potential, at least for many. I want to highlight a couple things from this model. One is in this region of the central area, note that there's actually few tributaries join Namok. And as we'll see, this in fact is true. We see very few tributaries joining Namok. But on the other hand, it shows many joining from the Greenland side. And in fact, we'll see that actually there are no tributaries that come in from the Greenland side. Well, Namok, I guess, was first identified way back in 1949 by Bruce Heason, who discovered so much of the Atlantic with echo sounding. This is not long after the development of echo sounders, in fact, and he employed them to great success in mapping, early mapping of the world's oceans, particularly the Atlantic. And he had 4 crossings only, but saw this channel, or canyon as he referred to it, and he hypothesized that this formed a continuous feature. In 1952, they went back out, he and Morris Ewing, and surveyed in much more detail. They had 80 echo sounding profiles, and some of how they characterized Namok actually is true even today. They identified it as 1,200 nautical miles in length. Its stream-like profile, they hypothesized turbidity currents were active within it. And this is not long after really the turbidity current theory developed. And they recognized it as a box-shaped channel with gradients on the order of 0.023 degrees, and hypothesized that it was mid-Pleistocene in age. I think they recognized that it was probably a relic system. Interestingly, they felt that there was an asynchronous basin uplift that accounted for the different height in the western bank as opposed to the eastern bank. And they suggested that the channel formed prior to tectonic tilt of the basin. Heason et al. In 1969 continued their surveys and published a paper in the Canadian Journal of Earth Sciences, recognized it as a 3,200 kilometer long canyon at this point in time, an average gradient now of 0.09 degrees. They recognized that there were no major tributaries to the channel, again, hypothesized Quaternary in age. They now recognize it's not a tectonic feature. In fact, they recognize now that the western levee was higher than the eastern levee due to Coriolis and not Coriolis sedimentation, and not due to tectonic uplift. And further argued that it was formed by erosion by turbidity currents. And they do recognize, however, that neither the source nor the sedimentary processes that construct the canyon were established. And in fact, they hypothesized that Hudson Strait seemed to be an attractive source because of the high amount of glacial-laden meltwaters that would stem from the northeastern Canada. And as we'll see, this seems to be the case. They also recognize that there are something like 20 telecommunication cables that span the canyon, and there were no sequential cable breaks that had occurred in the lifetime of the canyons, at least. So again, hypothesized that it was probably a relic system on that basis. In terms of the form of the canyon, Egloff and Johnson published a paper again in Canadian Journal of Earth Sciences and showed that the meander length versus channel width plotted well up in the spectrum in comparison to other channels. And so they suggest it's a fairly straight channel. And really the intense work on the Namok began in the late 70s, and really at the efforts of Reinhard Hesse, a professor at McGill University, and one of his early graduate students, and the first graduate student to work on Namok that I'm aware of was Sung Chao, and they looked at this channel from a sedimentological point of view, collecting cores, collecting seismic data, and really started to classify this system in some detail. Again, all based on profile data, though. The great water depths sort of precluded any side scan sonar at the time, and certainly predated any multi-beam bathymetry. So they argued for a meandering thalweg that worked through the system in the deepest parts of the channel, and they argued that there were point bars associated with the channel meanders. They indicate that the turbidity currents sometimes extended the entire length of the channel, and the natural levees, they categorize the natural levees, particularly the western levee, being higher than the eastern due to Coriolis spillover, and they hypothesize a broad floodplain along the flanks of the channel feature. They calculated an average gradient of 0.038 degrees, and infer that there's a possible tectonic control on the position of the channel. In fact, that middle figure you can see, in fact, what appears to be a basement high in this region. It's the former spreading axis, and whether there's a direct correlation or not, it's certainly coincident, but it's hard to imagine there's a direct correlation given the thickness of sediment there. So they developed a FASES model to go along with their sedimentological interpretations. And then in the early 90s, Hesse and others were able to employ a CMARC system. This is a deep, it's a shallow toe but deep side scan sonar system to work in, great abyssal water depths. And they imaged the channel in a couple of different sectors. And really what you get is a backscatter image from that. So they can't measure the metrics of the depth and so on, but they can measure the meandering channel and look at the sedimentological impacts of the channel and the channel migration and such. If we look at sort of conventional mapping, bathymetric mapping of NAMOC, this is a bathymetric chart, approximately in the year 2000, issued by JEBCO. And at that time, the bathymetric charts were still hand-drawn. And because they're hand-drawn and interpreted by an interpreter, they've actually recognized that NAMOC is a feature, and the contours sort of highlight the fact that there's a channel there. Though its course is somewhat interpreted between sparse soundings. In 2008, JEBCO moved to a gridded product, and the first grid was something like 60 arc seconds, or almost 2 kilometers in size. And so what we see is that where there are crossings, you get a little bullet hole, but there's not a continuous channel. So a coarse grid of this nature does not highlight the fact that there's a channel there. It takes an interpreter to recognize that. By 2021, however, the bathymetric sounding density is sufficient enough that they are able to produce a grid that's approximately 0.5 kilometer in size. And we still see in the northern reach, you see in the top panel, limited ability to resolve the channel axis. But where there's multi-beam data, you see in the lower right panel, you can actually follow the course of the channel much better. So where there are multi-beam data, you were able to follow the course of the channel. So this sort of provided the incentive for surveying. First of all, it's just such an amazing dynamic feature that has been not surveyed. Multi-beam technologies came on stream in the very late 90s, or very late 80s, earliest 90s. And yet even with 30 years of this technology being available, this channel still was not surveyed, which is quite remarkable. And so we wanted to survey it and really see all the dynamics in as much detail as possible. And of course, this can have implications for understanding fluid dynamics in a marine setting, in a deep marine setting. but also, of course, with that whole source to sink scenario, what elements are being carried with material that's being shed from the continents and ultimately deposited in the deep sea, not least of which is it a mechanism to bury carbon. And so this was some of the incentives. And of course, in the case of NAMOC, as compared to many other deep channels that have been studied, this is not associated with a major river system. It's not on a submarine fan. It's in the middle of a basin, deep marine basin. So what's unique about this feature, I think, is something that needs to be addressed. So I think we just go over this quickly, but the specific objectives, how did it evolve over time? What are the fundamental characteristics of it that can give clues to how the flow is operated within the channel axis? It spans 20 degrees of latitude. So what's the influence of Coriolis over a system like this that spans such high degrees of latitude? And, is it a carbon sink, or does it act as a roll to provide a carbon sink? And how does it relate to the ice sheet dynamics of the Northern Hemisphere glaciations? So we applied for ship time through the German system and were awarded the Maria S. Marian for 2021. We had approximately 40 days. And as I mentioned, we were able to successfully carry out a program despite COVID. The Marian is equipped with a multi-beam sonar. For those who aren't familiar with a multi-beam sonar system, a single beam is like an echo sounder on any vessel, whereas multi-beam emits many, many beams, and we're able to map a swath of the seafloor, many, many kilometers wide in deep water. Typically 4 to 7 times the water depth is the swath width. And we can map to a grid size of less than 100 meters in the Labrador Sea in those kind of water depths. And just an image of a shipwreck, or in fact, it's the caissons off Juno Beach off of Normandy, just to show the kind of resolution this kind of mapping can tell us. And we had also a parasound sub-bottom profiler, which gives us sort of an image of the sub-bottom at sort of 20 centimeter resolution. You see in the lower left panel there, and in the lower right panel, we also collected multi-channel seismic reflection data to see deeper underneath the earth and image the sediment thickness and top of basement. And we collected shallow sediment cores as well, targeting sort of the levees and the channel axis to try and understand some of the sedimentology associated with the channel. The Labrador Sea is known for its bad weather. This is sort of a plot of some of the average wave heights that occur in the Labrador Sea, and you can see the window of opportunity for operating is pretty narrow. July, August is the best time of year, obviously, and that's the time of year we were there. So we were fortunate in having that ship time allotted at that period of time, and we in fact had very good weather, mostly foggy, as you see in the upper left panel, but some sunny days, and people took advantage of those sunny days. So we managed to collect the 1,800 kilometers length of the channel. This is a sort of capture of what the multi-beam data, and the black lines overlaying the multi-beam data. The image of the seafloor are seismic or sub-bottom profiler data and seismic reflection data tracks. And I don't have the cores plotted on there. I don't recall how many cores we collected. Those are still being analyzed, and I won't address those in this talk. So this is the first sort of characterization of the channel based on all these new data. So we can plot in infinite detail now the channel axis depth and measure the gradients, for example. That's one of the fundamental pieces of information. So you can see overall the gradients range from 0.034 to 0.13 with an average gradient of 0.05 degrees. Now, to put that in perspective, if you walk 10 miles, you'll climb just 46 feet. So that's incredibly shallow angle. You wouldn't even notice that climb. So it's an incredibly shallow angle that it boggles the mind that turbidity currents could flow down such a low gradient and actually erode and carry sedimentary material at those gradients. This is an image of the channel just to see an overview of it in some detail. And to generate this image, I actually filtered the lower long wavelengths out. So I, in effect, removed the dip of the basin. You couldn't color code it because of the depth variability through the length of the channel that would give you any information about the channel itself. So I removed the long wavelengths with a Butterworth filter. And what you're left with here is sort of a flattened seafloor. And so you can see the intimate details of the channel. And in particular, what you see is the orange colors, what is the lower part of the screen, but the orange colors are actually to the west. And you can see that those represent a higher relative height as compared to the east side of the channel. And that is the effect of the higher western levee that is a consequence of Coriolis, the spin of the Earth driving material, apparently driving material to the west. In fact, the Earth is spinning underneath the material rather than actually being driven to the west. It's actually that the Earth is moving to the west, or to the east rather, and so it builds up a higher western levee. And this is an animation. I'll play part of it as we speak, but you'll get a sort of a view of what the profiles look like through the channel. So we've generated a profile every 100 meters in this case, and just made it as a playthrough. In essence, we straightened out the channel and are following the channel axis, and you can see the shape of the channel as it varies spatially down axis. And so the average width of the channel floor is about 3.3 kilometers wide, with some variability around that. Generally pretty consistent. It's plus or minus 1.1 kilometers, but you'll see in these profiles, it doesn't vary a whole lot. The average levee to levee width at the top, in other words, is about 8.5 kilometers, with a little more width, a little more variability at 3.15 kilometers plus or minus. And that's just the nature of how the levees are being constructed. The average depth of the channel is 114 meters plus or minus 38 meters. So the average depth is pretty consistent throughout the entire length as well. I won't, in the interest of time, won't play this full animation, but you get a sense of what the channel and the variability of the channel looks like. Sort of broad characteristics. It's a box-shaped channel. It meanders slightly. It has that high western levee. There's truncated reflections along the flanks of the channel. The tributary, there's a few tributaries, not too many. Is there a channel tallway? We'll look at that. Are there point bars? We'll look at that. And there appear to be some nick points along the axis, which we won't get into the flow dynamics that cause those in this talk, at least. In terms of seismic and sub-bottom profiles, we see onlap of the western levee onto the margin on the Labrador side, where the eastern levee is typically quite flat. We see slumping from the walls, quite common slumps from the walls of the channel into the channel. And I think this plays a significant role, as we'll see, in terms of the sediment dynamics, slumping from both sides of the channel. And you can see in the lower right panel what's interpreted as a slump of the channel wall into the axis. And we also see on the seismic profile in the upper left that there is evidence of NAMOC being buried and through time, and that they actually geographically coincide quite well throughout the length of the channel. So there seems to have been very little migration of the channel through time. This is one of the few points where we notice a tributary further down axis rather than at the headwater areas. And this channel, though, is buried. We see it where it enters the channel axis, but then it's quickly buried to the west, to the left side of the screen there. And the sub-bottom profile shows that channel that's then buried under debris flows. In fact, this is the headwater region, And it looks like it was also buried under massive debris flows, probably late stage in development of NAMOC. It was subsequently buried, and NAMOC seems to be trying to restore itself here, as you see this very narrow channel trying to cut into that debris flow. So it looks like NAMOC was trying to recover itself after being buried by massive, an episode or episodes of massive debris flows. And you can see in the lower left panel, a perspective view looking up the channel, and this very narrow channel cutting up further through that debris flow, and a tongue shape through the axis of the channel of debris flow material. Some sub-bottom profiles along axis or along the length of the channel, sort of flanking the channel. We see debris flow, evidence of debris flow bearing sort of late stage of the channel development, bearing much of the lower relief regions. And, you know, is this related to perhaps outburst flooding in the last phases of the glacial period? It may be. I think that's an hypothesis we need to test. It's a pretty interesting scenario to have such massive amounts of material shed and as debris flows that flowed throughout the whole Labrador Sea. It's quite an interesting, perhaps an interesting phenomena. So our interpretation is the headwater regions are actually Hudson Strait and glacial outwash through the Hudson Trough, and that these main feeder channels generated NAMOC, and we don't have multi-beam coverage right to the edge, so or sub-bottom coverage. So that's something I think to do in the future as well. If we go to the other extreme end of NAMOC, it's quite interesting. So we don't have full multi-beam coverage, but this is a transect that we collected in 2015. And we see NAMOC at the outer edge of Newfoundland Ridge here, where the circle, the red circle shows. And it's still, even 3,800 kilometers downstream, a box-shaped canyon that's several kilometers or you know, several hundred meters deep and several kilometers wide, even at its most distal appearance. So it's incredible that it has restored this shape throughout its entire length. Unfortunately, beyond this point, we have no data to suggest what happens next. We don't know where NAMOC goes or if it just sort of fizzes out. There's certainly no obvious fan-shaped deposit at the end of the feature, so we don't know what happened to all that material. So now let's look at this river analogy and the meanders, the Alwags, and point bars, and see if there is an analogy to other river systems or even submarine fan systems. So here's a plot all to the same scale of NAMOC, the Congo Canyon, and the Mississippi River. Now you can see some dramatic differences visually right here. First of all, the channel is much wider than sort of a typical submarine fan channel, as we see comparing it to the Congo Canyon. We also see that it meanders very little compared to these systems, and these are some important criteria. If we look at these meanderings, we can measure sinuosity, and it's basically the ratio of the curvature versus the length, and we see that for NAMOC, this ratio plots to a 1.02 to 1.06, very small amount of sinuosity. Compare that to the Congo channel, which is 1.23 to 1.68, or even to the Mississippi, which seems to be on the order of 1.4. We see that the NAMOC is actually quite a straight channel. And I show a plot in the lower panel here from Sylvester and Perma's publication 2017. They're comparing it to latitude, but just looking at the sinuosity values starting at 1 and going to 5, you see NAMOC is all down around 1, the value of 1, whereas these other systems have sinuosities that extend significantly higher. So a very straight channel by all comparisons to other features. In terms of the Talweg, it was hypothesized or argued by Chow and Hesse that there was a continuous sort of meandering Talweg throughout the channel axis, but our evidence doesn't show that. When we have full multi-beam coverage, you see this automatic plot. The yellow line here in this plot is the Talweg, the deepest part of the channel, and it flips back and forth. So it doesn't seem to be a meandering feature. It's discontinuous at best, if in fact it is truly a Talweg, a sedimentological Talweg, that is. So there's no obvious continuous Talweg in the axis. Where we do see what could be interpreted as a Talweg, I believe it's because the channel flow is being pinched to one flank or the other due to wall collapse of the channel. So in this case, we see an example where the slumping into the channel has presumably forced any subsequent flows to be focused on the opposite bank. And I think that's what we're seeing for the most part, is that these channel wall collapses are pushing the flow to one flank, and rather than being a sedimentological feature or a hydrodynamic feature, rather, it is actually just because it is confined by channel slumping. Again, if we look at point bar development and compare that to river point bar systems, again, I think it's quite different. I think we're seeing, rather than conventional point bars that are developed through hydrodynamic processes, I think what we're looking at is actually channel wall slumping that is actually creating these small meanders by forcing the flow to one flank. And if we look at seismic or sub-bottom profiles of what are called point bars by earlier researchers, we don't see any tabular cross bedding development. What we see is what seem to be slump deposits that then may be subsequently reworked by channel flows, and we see some bed form development on top of these features, but we don't see any of the structures that could be characterized as point bars. So I don't think there's clear development of point bars. I think there's channel slumping that is then being reworked and is actually forcing or developing of the small meanders. So if we compare like a river flow to a turbidity current flow, the hydrodynamics, the physics are extremely different. So why should we expect to have these structures that compare to river flows? In a river, an open channel flow, the velocity gradient looks like the red line here, whereas in a turbidity current flow, the high velocities are actually closer to the bed. Ingo Kloka did some numbers on these when in his studies in the 90s based on grain size analysis. He felt the mean flow velocities probably averaged about 0.86 meters per second, but there's strong vertical gradients and almost a detachment from the basal flows versus the surface flows. So he maps or suggests 8 meters per second at the base and possibly 0.45 meters per second at the top of the flow. Turbidity currents are driven by gravity, but are really a function of the density contrast, and as opposed to open stream current velocities, which are really driven by the volume of water flow and the radius of the channel axis. Cloak estimates that densities probably exceeded 87 kilograms per cubic meters at the base. That's a really dense flow, and probably 4 kilograms per cubic meters at the top. So in the interest of time, I won't go through all of this. We have a little bit more to discuss, and I want to end on time. But the comparisons are, turbidity currents are really event flows, whereas river currents are continuous. So even if we compare to sedimentary fan channels, they are periodic, related to monsoons and storms, whereas turbidity current flows are likely episodic without any real periodicity, and so there's many other comparisons there that I'll leave for digestion later, but there's some fundamental differences, the point is, and why should we expect the characteristics to be the same? since the physics and other mechanisms are quite different. So what are the source to sink implications? This is a glacial feature, it seems, largely related to probably at least the last glaciation and likely all 5 last glaciations of the Northern Hemisphere. And so they seem to be related to massive glacial outwash periods where glaciers have washed material into the sea via hyperpycnal flows and density flows, and including, nephloid plumes, and, just massive amounts of materials are dumped in a short period of time into the deep sea. And these allow the formation of features like NAMOC. So we see along the Labrador margin evidence of many channel cuts along the upper slope, and these feeder channels feed into the NAMOC system. This dominance of turbidity currents actually produces a rather exponential decay curve shape to the continental margin, and we see in the seismic profile this exponential decay, this bowl shape, and you see NAMOC off in the far extreme right of this image. So assuming that the sort of the natural state for a continental margin is this exponential decay shape, I wrote a paper in 2021 where I modeled this shape for the continental margin using as inputs the continental shelf and the deep ocean floor, and modeled a continental slope based on this exponential shape, and then subtracted that from the actual bathymetry. And lo and behold, what's left is what is anomalous to that shape. And what is the principal anomaly is contorite deposits. And so we see the massive Blake Ridge in the lower left corner here. We see the Chesapeake and Hatteras drift systems off the US margin. We see drift system off Nova Scotia. The Laurentian fan is a massive anomaly. We see drift systems off Newfoundland, and even in the Labrador Sea, drift systems such as Hamilton Spur. So these create anomalies. So clearly, contorite geostrophic currents played a massive role in redistributing material that's shed from glaciers and such. It distributes them all along the margin. Vast implications for source to sink. So in this case, they were probably material in suspension that's then carried by these geostrophic currents and carried, thousands of kilometers possibly to ultimate depositional sites. Massive implications for source to sink in that scenario. But could NAMOC then be a short circuit, particularly for bedload or near bedload material transport? And it likely was. And it has resulted in transport of material, again, thousands of kilometers distal from where the source is. And it presumably transported a significant amount of material down the axis of the channel and out to the Somme abyssal plain, but we don't see a sedimentary deposit at the mouth of the of NAMOC. So it raises the question: where is the sink? Again, massive implications for source to sink scenarios, and worthy of some study, I think. So summary and conclusions then. NAMOC is a glacial outwash channel. It's presumed to be extinct. We are hoping to get some current meters down into the channel axis as we speak that could then tell us whether it's an extinct system or if there's any activity at all. It acted as a sediment pathway for presumably bedload and near bedload, suspended load, density currents, for example, via turbidity current activity. Its physical characteristics are really unlike any other sedimentary system. Its analogies to a river system is not appropriate. It's largely a constructional feature and not erosional. It's created by turbidity current activity. It's presumably episodic. It's influenced by Coriolis in a strong way. At least the levee deposits are. And its analogy to channels of deep sea fans are not really suitable. Again, it's episodic versus periodic. It has multiple sources rather than a point source, and it transects a large latitudinal gradient. Since Hudson Strait was a major ice outlet corridor that drained much of eastern North America, then Namok was likely a major corridor for sediment transport from a massive geographic hinterland. I mean, most of eastern North America, including the northeastern U.S., is potentially a source region for this material. And tracing sediment from source to sink is complicated, as shown. It's event driven, it's influenced by geostrophic currents, and there's no obvious sedimentary deposit which can link the sink to the source. So with that, I'm going to end. I'm going to play this little video as we talk. Feel free to ask some questions while this plays. This is just a fly through to give you sort of a perspective from north to south, a fly through down the channel axis. So Paul, I don't know if that can play while we ask questions.
Sure.
You, but
Yeah, that's good. Okay, thank you, David. This is fantastic talk. And so let's say to the audience, if you have any question, please go ahead. You can unmute yourself and directly ask David.
Hi, David. It's Don Forbes here.
Oh, hey, Don.
I saw the article in EOS, and then this is a great presentation. Fascinating system.
Thank you.
I've got lots of questions, but I guess one of the questions is the buried channel. And can you trace it appears to be a separate channel rather than a continuous. At least the image that we saw, it looked like there was a buried channel and then there was sediment and then the present Namok. Can you get any estimate of the age of that buried channel from the lateral stratigraphy?
Yeah, that really hasn't been worked on yet. First of all, I have to say, Don, I think I was a summer student for Don when I went out on that 84 survey to investigate.
We go back a long way.
Oh, we go back a long way. Yeah, exactly. Yeah, that really hasn't been studied well yet, Don. And what are the linkages to the modern channel? Is it a completely separate system? None of that's really known at this time. The new multi-channel data hasn't been studied much at all yet, and it's been recognized on older profiles, but most of the older profiles are pretty poor quality. And so the newer stuff is good quality, but there's only a few crossings. There's a significant amount of new industry data out there that was collected by the Newfoundland and Labrador Oil and Gas Company. And whether we could get access to that and have a look, it's a good project, that's for sure. But I can't say much about it at this time. I don't really have much to say. There's obviously no deep water boreholes. There's a couple IODP holes that don't correlate well to the channel. They were collected for paleoceanographic purposes, so it would be tough to get an age control on it. But
thanks.
Yeah.
Okay, great. Anybody else? Go ahead if you have any question. So
well, let me ask another one then.
Go ahead.
I guess the question is, how the idea might be that deeper channel is related to an earlier glaciation. What's the possibility that accelerating melt from Greenland, for example, might reactivate the channel?
Yeah, it seems like Chow's interpretation was that the Greenland side, the eastern flank basin, was a floodplain, but in fact, it seems as though it's a different system. Surprisingly, the sparse data that we have seem to indicate that there's really a braided plain system on the eastern flank, and likely that's responsible for what came out of Davis Strait and off Greenland, and we don't see any channels reaching from Greenland all the way over to Namok, except south of Greenland, south of Erik Ridge. We have the IMOC, the Amarsuik mid-ocean channel, and it's a braided system. It's a braided stream system as well. I should have shown an image of that. We have some great new data at the conjunction of IMOC and Namok, but it's a braided system, and we see it feeding into Namok south of Erik Ridge. But other than that, north of the Erik Ridge, we don't see any evidence of material from Greenland feeding into Namok. So I don't know if increased melt from Greenland would actually make it out to Namok, and you would see some increased activity. That would be neat to see, but we don't see at least a historic connection through the rock record or geologic record. But yeah, those old channels I expect predate glaciation or predate the Pleistocene glaciations. They may be related to Miocene glaciations perhaps or something, but I would expect those to be Labrador Sea stopped forming in 60 million years to 54 million years ago, something like that, and so has been filling up with sediment since. So those sediments being close to basement are likely younger than 50 million years, but probably Oligocene, Miocene in age. So
Dave, the other question in your talk, you kind of now clear, the trigger, the source of, the cause, even this deep channel. But how does this long channel or river valley end? I mean, when they end, you also point out there's no sedimentary deep sea fan. Oh, I mean, there should be somewhere. I mean, those material transferred ended somewhere. I mean, the sink part. Is any hypothesis, anybody talk about that?
There needs to be a really good study in that region. There's very, very few data out there. Maybe Don knows. I understand Dale Buckley ran an expedition out in that region many years ago, but I'm not familiar with any publications or results from that. Maybe Don, you have some ideas, but there needs to be a study there. It has to go somewhere, and unless it's totally fluidized by that point in time and is spread throughout the Somme abyssal plain. But Don, do you know any insight, any survey?
I think Dale's work was pretty much all cores, and it was related to radioactive waste disposal as a concept that you might bury that in the sea.
Right.
So no, I don't think.
Didn't address that.
You need more of that ship time.
Yeah,
need to go explore that end.
Yeah.
I mean, it would be not surprising if we found something like a deep sea fans, may already modified already, but still should be something deposited in much deeper in the water or at the end. Yeah,
you would expect so. There's just so few data out there. I mean, I expect even the JEBCO chart is based on few actual bathymetric soundings in that region. So yeah, definitely needs to be follow-up investigations, no question.
Okay, very good. Okay, next question. So go ahead, Valentin. Yeah.
Hi, everybody. Hi, Dave. Thank you for the very cool presentation. So I have basically maybe two questions, one slightly more scientific than the other, I guess. But so the first one, how do you explain this lack of I don't know if lack of sinuosity is a good term, but the very straight planar morphology of this canyon? And second, maybe, do you think that this is truly one of its kind on Earth, or do you think there are potentially some other similar features, and like maybe on the eastern side of Greenland, between Greenland and Iceland, for example?
Yeah, there certainly are smaller systems that have been recognized. I mean, you know, we still only have something like 25% of the ocean floor map, so there's still significant areas to cover. We see a couple of channels, for example, in the Arctic that are deep sea channel systems that are likely glacier fed in this fashion. So there could be some comparisons to be made. They're much smaller systems, though. So I don't think I don't know if there's another equivalent system that is of this scale. That's for sure. As to its sinuosity, that's something we hope to address, or lack of sinuosity. That's something we hope to address. It's no doubt related to flow velocities, and so, you know, extremely high velocities presumably are flows are less meandering than slow velocity flows. So that's probably one element. There certainly is no relationship in meandering related to latitudinal change, in other words, Coriolis. So I think the principal driving factor is flow velocity, which in the case of turbidity currents is flow density, is the driving, you know, really the driving mechanism. So they must be very high density flows that flow at great velocities to keep the channel fairly straight. That's my supposition, and that's why we're working with guys like Chris Stevenson, who's more of an expert in these matters. Thanks.
Any other? Dave, other question, you know, it is easy understood, you know, on the slope. I mean, the gravity or turbid flow cut slow those channel, but in a relatively very flat, deep ocean flow, what's the mechanism? What's the driving force for those? You know, is it deep sea current, or I mean, what?
Well, it's ultimately gravity, but you know that portion of gravity at such low angles is a very small driving force. So it's the density relationship, the density current, which can flow on extremely low slopes. It's incredibly surprising. I agree. It's amazing, particularly that it flows 3,800 kilometers and maintains that same morphology. So the flows clearly have maintained their properties for such long extents over such shallow gradients. It's crazy. It just speaks to the really interesting aspect of this channel system. But you know, we know flows on river systems on deep sea fans. I mean, the gradients are quite low. They're incredibly low. Something like the Bengal fan is comparable to the Labrador Sea in terms of gradient. So we know that this happens, but the driving mechanism is gravity and the density relationship.
Okay. Very good. Anybody else? Oh, there's a question in the chat. Dave, are you able to see? Is ask you, I mean, it's a beautiful picture. Which kind of software you use to draw the, I guess, I believe the multi-beam seafloor?
Sure. All of this was done in ArcGIS and ArcScene. I think I made the animation in ArcScene, and all the images are generated in ArcGIS. I did the filtering in GMT, generic mapping tools. Arc doesn't have the Butterworth filtering capability, but so I did that in GMT. But otherwise, it's all done in Arc.
Okay, wonderful. Any other comments or questions? If not, it's the 10 o'clock East Coast of US. And Dave, thank you very much for this fantastic talk. And many of us read your article in years, but this talk gives us a much more detailed, a great perspective. And I think it give us another very unique view from source to sink point of view. That's wonderful. Thank you, David. So also are looking forward, to see you, many of you, next week. Janek talk about a little bit deep time of the Delta system. So, okay, and if no any other comments or questions, we can end it here. Okay, great. Thank you, everybody.